We'll wait a couple of more minutes for people to join, and then we can start. Good evening. This is NPTEL course Applied Thermodynamics. This is a problem solving session, and this is week 1. So we'll have 12 weeks. This is starting with week 1, and the course instructors are Niranjan Sahu, professor, and then Professor Pranab Mundal. They are from IIT Guwahati, and I am Bharat Aditya, PMRF PhD scholar in IIT Madras. So I have some problems similar to the assignment problems which I've kept, and I also have a descriptive problem. We'll see, and if you have any doubts, you can ask me over the. So we'll move on. So the first question is, we have a free expansion process. So we have given options. We have been asked to choose the correct statement. So what will happen to heat and work transfer during a free expansion process? You can have it as an interactive session. You can type it in the chat box, and you can verify your answers are correct or not. So it'll help you in the process. Well, you can, if you have any doubts, you can come back and ask me. So we have a free expansion process. Free expansion, there is no restriction to the process. If you if you have a vacuum, you burst a balloon inside the vacuum. So there's kind of an example of a free expansion process. So in that case, what will happen to heat and work transfer? So in this case, the options are the total work done is 0, the total heat transfer is 0, and we have work done is 0, but heat increases. There is an increase in heat, and increase in heat means there is a heat transfer happening inside to the gas. And statement A and B are both correct. So in this case, the answer is option D, both statements A and B, because there is no restriction happening. So the work, the free expansion, it's not doing any work. So this work done is 0, and there is no heat transfer happening because the internal energy of that gas will remain same. So being work done is also 0. The heat transfer which is taking place will also be 0. So the answer is option D. So next question is, we have on a hot summer day, a student turns his fan on when he leaves his room in the morning. So when he returns in the evening, that what will be the room's temperature? So assumption is that all doors and windows are kept closed. So we have shown you image depicting that. So we have a assuming this is a room of the student and the fan is running, and assuming that it's isolated, there's no doors and windows, uh, so there is no transfer taking place. So what will happen to the temperature of the room inside? So it will become cooler. Option B, it will become warmer. C, there will be no change in temperature. And D, it cannot be predicted. So you have a fan, it's running. So I'll give you a hint. It's like, consider this as a black box. There's something going in, but it's not coming out. So what will happen to the system? Okay, the answer is it will become warmer. So the why it becomes warmer is, you assume this room is a system, and for the fan being running, you need to supply some work, and you supply some work, so the energy is going in. So this energy, what will it do is, it will get dissipated in the room, and that energy is not going out anywhere else. Even if it has to go out, it will be negligible, and to the point where it reaches steady state, the room's temperature would have risen, because you are constantly supplying work to the fan for it to running. So that energy is dissipated in the room. So that you can see from the first law, there is a E in, energy in going out, energy out. There is a change in the energy of the system. So the E in, energy in, is the work done on the system, and which will cause your internal energy of the system to change. So for if this work done is positive, because you are giving in an energy, so the temperature T2 will be larger than the T1. So the temperature would have risen compared to the morning temperature. So the answer is option B. So moving on, we have the density of water is maximum at 4 degrees Celsius. So the answer is option A, true, or option B, false. So water behaves peculiarly till 4 degrees Celsius, and after from 4 to 0, it will have it behaves differently compared to any other normal fluids. So true, the answer is option A. You can see I've plotted a density versus temperature curve. You see the density goes to a maximum and then decreases. So on reduction of a temperature, the fluid freezes and the density goes up. So that's what happens after 0 to 4. In case of water, it starts decreasing. So the answer is option A, true. So the next question is, if you have any doubts, you can ask me with the previous, or else I'll move ahead. Or not, if you can ask any doubts if in the sessions also, if you have any doubts, you can ask that as well. Okay, so the next question is, which of the following thermodynamic parameters are considered as intensive property? Also, if you are not hesitant to use the mic, you can type it in the chat box. Okay, which of the following thermodynamic parameters are considered as intensive property? There are two properties, intensive and extensive. So in this case, we need intensive. The options are A, specific volume, B, mass, C, volume, D, internal energy. So intensive property, you can remember it like the intensive. So you can say that it's independent of mass. So you can say, even if you split, if you have some fluid, If you see, you split it into two parts, and if the property of that fluid doesn't change, that is an intensive property. If you split it into two parts and you change the proportion, you see that the property also changes, then it's an extensive property. In this case, we have been asked intensive, which is independent of. So we have options: specific volume, mass, C volume, and internal energy. So the answer for this is option A, specific volume. Specific in sense it's divided by mass, say per kg of mass or whatever. So it's independent of mass. So mass, if you split that quantity into two, the mass of each of the quantity will be different. It will not be same. But if you see specific volume is like density. The density of water, if you have it in a big bucket or a small bucket, the density will be the same. But if you see the volume will be different. And so goes for the internal energy also. If it would have been a specific internal energy, then you say it is independent of mass. If you have specific word, it is independent of mass, so it will be an intensive property. So I hope you remember the types of system. We have three type of systems, and based on their mass interaction and energy interactions, they are classified into three. We have isolated system, we have closed system, and we have an open system. So here I have shown three examples of systems. So you have a hot cup of tea on a so that is one case, and you have a lid placed on the cup, so that is another case, and you have a tea in a thermos flask, so that's the third case. So these are three examples of the three systems. So in case if you put it in a thermos flask, there is no heat transfer. In this case, everything will be work transfer is zero. You are not doing the fluid, or you are not doing any work on the fluid. So work transfer is zero. So here the only energy transfer which is happening is the heat transfer. And in the thermos flask, in the ideal case, you are expected to have, there is no heat transfer happening between the fluid and the environment. And so in the thermos flask, the tea which you are kept hot is expected to be hot. So there will be no heat transfer, and there is no mass transfer happening because this is enclosed, and the quantity of this thing will remain same. And the second, if you see the second case, you have a cup of tea, there's a lid placed over it. So in this case, the heat transfer can happen on the cup surface or on the tea. So there will be heat transfer, but there will be no mass transfer. So there is during because of evaporation or the other the water getting or condensation or whatever happens, it will not be there. In this case, hot, so the fluid will try to evaporate. There will be a mass transfer. So that doesn't happen in the second case because you have kept a lid over it. So this is an example of a closed system. And you see the first case, you have a hot cup of tea and there is no lid over it. So there can be a mass transfer as well, and there can be a heat transfer as well. So this is an example of an open system. So I've also put you can see an image. This is like a storage vessel for LNG, like liquefied natural gas. So what do you expect this to be? Option A is an open, option B is a closed, option C is an isolated. So we'll see it in three cases. So first is like the yellow part is the insulation of the storage vessel, and inside you are keeping the liquid nitrogen, natural gas at minus 160 degrees Celsius. So what do you think this would be? Is this an open system, closed system, or an isolated system? Okay, so if you see, this is similar to the thermos flask. You have insulation because you are keeping it at minus 160 degrees Celsius. So if you have a normal vessel without insulation, you will have environment will be at higher temperature, 30, 40, 45, 50, whatever. the environment temperature will vary, and that is very large compared to the temperature difference is very large compared to the liquefied natural gas. So the liquid will take in heat from the environment and it will start heating up, it will evaporate. We don't want that. We want it to be stored in energy form so that it can be transported and so on, used it for other purposes. So you use insulation and it's expected that it remains same. So this will be an example of an isolated system. Thinking that if it's not an ideal case, if you think this is not an ideal case but the insulations are bad, then this will become a closed system. I hope I'm not confusing. If it for an ideal case, you expect it to be an isolated system, but normally that doesn't happen. The insulations are bad. There will be some amount of heat which leaks in. So in that case, it will become. It's all based on the assumption. In the first assumption being an ideal case, it will be a isolated system. Assumption being that it's not an ideal case, it will be a closed system. And if you see the closed system, in all the actual cases, what you'll have, you also have a pressure relief valve or other system. So when pressure is existed, you can also have mass transfer, and if you are taking it out, there can be a mass transfer. In that case, it will become an open system as well. So based on the assumption, you can keep it, you can classify it to the systems. I hope this is clear. Okay, moving on. The sum of heat and work transfer will be 0 if a system returns to its initial state having gone through series of processes. You have asked me whether it's a true or false statement. You are asked the sum of heat and work transfer will be 0 if a system returns to its initial state having gone through series of processes. Don't confuse it with respect to the signs of work and transfer. It will become more complicated. You assume that this simply states that the amount of heat which you put in and the amount of work which you put in or you get will be equal. The total amount of heat and the total amount of work will be equal. So that is 0. So if a system returns to its initial state, it is going through a cycle. So the system is returning to its initial state. If you see, this is just a twisted statement of the first law. So if you see, the system returns to its initial state, so it has gone through a cycle, and for any cycle, the property of that system will be same if it has reached its initial state. So if it has gone through its cycle, the property, there will be no change in the property. Being internal energy being the property of the system, after reaching its initial state, there will be no change in the internal energy. So this will become 0. So the sum of heat and work will be 0. So the amount of Q and some amount of W will be same. So I got a question, which is the okay. The references, I hope it will be given in the course. If you see the course recommendation syllabus, you will have the recommendation of book as well. I'll also go through if something is there. I think it's better to follow those books suggested by professors. Okay, I'll move on. So if the yeah.
So here for delta U will be 0, but then delta Q will be equal to W is net. So when we sum it, it should be it shouldn't be 0, isn't it? Actually, in that equation, Q minus W equal to 0, but here the sum of heat and work is asked. So can it be 0?
Yeah,
It's just asking just
what happens is this system is going through a cycle.
yes,
So
sir.
the sum of heat, say there will be some heat addition and there will be some heat rejection, and there will be
Yes.
also some work addition or work. So this sum of works and this sum of heat which is taking place will be equal. When the system goes through a cycle, this will be true.
So by meaning the sum, we don't need to consider it as actual addition. We just need to check give the property as zero and rearrange the equation.
Yeah, this is true only if this is reaching initial state. The same, then your property will any property will become zero. It has to be a property of a system, like internal energy or enthalpy or entropy. Entropy, you should not confuse. Entropy of system is different, and if you considering entropy generation and so on, that will be different. The property of the system will remain zero if it change in property of system will remain zero if it goes through a cycle and it's reaching its initial state at the end of the process. So to give you an example, can take any example. You refrigerator, or if you have refrigerator, you are giving in work, and you have you are cooling the cabinet, but you also rejecting heat outside to the atmosphere. You have condenser. If you see, there's a heat exchanger behind a fridge, so that will reject heat to the ambient, and you're cooling the cabinet inside. So you're taking in some heat, putting it out to the environment, but this difference will be equal to the energy supplied by you. So that will be true in any case. If it goes through a cycle, this amount of Q supplied, it will be amount of work done.
Okay, so it can be also considered for the engine that
Yeah,
delta U will be zero.
any process going through a cycle, this will be true.
Okay, so
Okay. So similar problem, just like the second which we saw, there is a fan rotating inside the room. So this is, in this case, if the door of the refrigerator is kept in a room which is left open, so you have kept the door of the fridge open, and what will happen in that case? You have a room, assuming there is no window or anything open, so the room is there, you have a refrigerator inside, you have kept the door open, and the refrigerator is running. So what will happen in this case? The temperature of the room will gradually increase. There will be no effect in the room temperature. The temperature of the room will decrease to the refrigerator temperature, any of the above depending on the refrigerator type. I just now gave an example of the refrigerator, how it's happening. You are cooling in the cabinet, but it also rejects heat at the behind, and this sum of difference in the heat will be equal to the work supply. I'll give it as a hint. So you have the refrigerator running, and this is just like synonymous to the example we saw on the second problem or third problem which we saw, the fan running. It's just a similar problem. Yeah, assume this room as a black box. See what kind of heat transfer or energy transfer is happening.
So in this case, when we open the system, then the region it need to cool, it will be the whole room, isn't it?
Sorry, can you come again?
If the refrigerator is in open position, then the region which it need to refrigerate or cool down will be the room itself, isn't it?
Yes.
Okay.
So if you see, in this case, the temperature of the room will gradually increase. Why it happens? See, assuming this whole room is a black box, you are supplying in work or energy in form of electricity. So that is equivalent to work. So what you are supplying in energy, but that energy is not coming out. So what this will do is, this will increase the system's temperature. You may say that this refrigerator is cooling the whole room. I gave you a hint. There's the refrigerator will cool that inside cabinet, but it also rejects heat at the behind with the heat exchanger which is at the behind. This heat rejected is actually greater than what the Q is taken from the foods or whatever you kept inside the refrigerator, because this difference should be equal to the W, the energy supply from the first law. So what happens is, you are supplying in the energy, but this energy is not going out anywhere. This energy is going inside the room, and the room, from there you are not losing any energy. So if you are supplying in energy eventually or naturally the system's internal energy or energy of the system will go up. If the energy of the system goes up, so the temperature of the system also will go up. So just that, just to confuse you with that refrigerator and fan, because there's just the fan running here, you will think that the refrigerator is a lower temperature, so the temperature should reduce. So not the case. Here you are supplying in work, that work will increase the temperature of the room. I hope I'm clear. If you have any doubts. Okay, so I think it's clear. So I'll go ahead. So exergy is the minimum amount of work of a device can deliver without violating the laws of thermodynamics. So that is a statement which has been asked whether it's true or false. Exergy is the minimum amount of work a device can deliver without violating the laws of thermodynamics. I hope you remember the definition of exergy. That will give you, it's a straightforward answer. Okay, the answer is option A, option B, false, because this is exergy is maximum amount of work. There's no minimum. The maximum amount which you can take from any system is the exergy. It's defined such that you have suppose you have a system at temperature 300 or so, assumption, and the dead state is the your environment state, what you your ambient, what current situation is. So you can bring the system to that state. It cannot go below that. To go below, you have to do work. So that cannot happen. The system can reach this dead state. So this during this process, assuming that the process is reversible, the work which you get will be the maximum which you can obtain from the system. So that is called as exergy. So that's what I have defined written here. A system delivers the maximum possible work as it undergoes a reversible process from the specified initial state to the state of its environment. So that the system going from the initial state to the environment state, the maximum possible work which is obtainable during a reversible process. So this is called as exergy, and this environment is called as dead state. So this represents the useful work which you can actually obtain. This is an ideal case. You cannot. So that here the assumption is the reversible process. So this is an ideal case. You cannot actually get that much amount of energy. It will be lesser than that. Assuming that it's an ideal case and all the process is reversible, from the initial state to the dead state, you will get the maximum possible work. So the statement is false. Yeah.
So by meaning the dead state, is it the equilibrium condition or anything?
Sorry.
By saying the dead state, does it mean that it's in the equilibrium?
Yeah, you can tell that the system has reached in equilibrium with your environment. So that is it. It's reaching your environmental state means it will come to eventually to an equilibrium.
Okay, so here if it's irreversible, then will there be any X energy? Like there is a formula for entropy and X energy.
Yeah, you have a formula for exergy. I think it will be explained in the class. I think. See, exergy is it comes from second law. So assuming that you give there is a whole exergy equation, exergy in, exergy out. For open system, it will be H minus Ts, and also you have to calculate the entropy generated. I don't know. I have to write.
So this H minus T is actually Gibbs energy.
Which one?
H minus Ts is actually Gibbs
Yeah,
energy,
in
isn't
this,
it?
the temperature is not the temperature of the system, it's the temperature of the environment.
So
It's like
it's exactly
the
and Gibbs energy
maximum energy difference, and the T naught, the S is the entropy. So during a process, the process will not be, there will be some entropy generation. So that will reduce the amount of work which you can get from system. So the first law says that the energy in and energy out will be same, right? So the energy will be same. But when you talk in terms of second law, you have the quality of the energy as well. So work is at a higher quality than the heat. Heat at very high temperature is higher quality than the heat at lower temperature. So uh, you can calculate, assuming the temperature at the ambient is T naught. What you can say is, if there is you are supplying a I think I'll okay. I think it's better as you watch the video. I'll create a slide for you the next session. Is if it's okay for you.
Okay, sir.
I'll create an exergy slide for you. I'll put it in. Uh, I'll add it in this the PPT as well to for you, and I'll also explain it to you in the next week.
Okay, sir.
Because see, the idea is you have exergy is the maximum amount of work which you can take. So that's the general idea.
So, so if the system is reversible, then if we multiply that efficiency for an engine case, if we are multiplying the efficiency with the heat supply, then it's actually exergy, isn't it? Useful work, isn't it?
That is the work actual work which you can get.
Okay, sir. So that can be only used
Exergy,
for the
see,
reversible
that's what
systems.
this actual work is just a part of this exergy. Exergy is, it just says you have to an initial state. If you from that initial state you come to that state, this much amount of energy is the maximum amount which you can get. You cannot get more than this. But in the actual case, this will be lesser. This all happens because of the entropy generation, the friction, and other stuff. So that will reduce your efficiency of the system. So that work will be lesser than this exergy.
Okay,
Here the
sir.
assumption that it is a reversible process. So it
So,
yeah,
so you said that the work will be inside the exergy. I mean, it will be subset of that exergy, or
yeah, you can say that.
okay, sir.
You can the other part is like uh, it's due to the entropy generation that is given as T naught and S gen. So you can say exergy is equals to the actual work which you are getting plus T naught into entropy generation. You have to calculate this entropy generation.
Okay, sir.
This is exactly an exergy equation in the simplified form. S gen, you have to calculate entropy generation for a reversible process. How what is the system entropy? You have to do an entropy balance basically, and calculate the S gen, and you have the actual work. This summation will be equals to exergy of the system. Yeah, the maximum exergy work you can obtain.
Okay, sir.
Okay. Uh, so moving on, we have what will happen to the temperature of air coming out of a punctured ball. So a football is filled with air and there's a puncture. So what will happen to the air which is coming out of this hole? It will become hotter. B, no change. C, becomes cooler. D, uncertain. Yes, the answer is it will become cooler. Why it cools? Because can assume that is an expansion process, or we also call it as a Joule-Thomson effect. Joule-Thomson effect is it's like you have a small restriction hole in when the fluid, high pressure fluid passes. Normally, except uh, hydrogen, helium, and neon, the other fluids will cool on expanding. When there will be reduction in pressure, so this expansion process will cause reduction in temperature. So this will become cooler.
So
Yeah,
this fuel compress effect is called the throttling, isn't it?
yeah, it's called as throttling.
So, so I have a doubt that for the throttling it will be an isenthalpy process, isn't it?
Yes.
But for nozzle also the area is reducing, but we are getting another formula for that. I mean, in the form of V1 and V2 when we apply the steady flow equation. why it is we are getting two equation for that. I mean, for the throttling, we are actually narrowing the uh, dia. Also for the nozzle, also we are narrowing dia. In the nozzle part, we are the pressure energy is converted into kinetic energy, and we are getting velocity,
Yes.
increased velocity. But here we are getting uh, isenthalpic process, and the formula there is no velocity term or any assumption
Yeah,
for this case.
you can do it based on, you can do a velocity balance as well, but in this case most of what happens is the majority of the energy is consumed by the gas itself to reduce the pressure. When the pressure is reducing, so in that case what happens is converted to the velocity, but in this case it the gas itself which consumes that energy to change for the expansion process. uh, Assuming, see, what happens during expansion means your volume is expanding. So
Yes, sir.
if volume is expanding, it means it needs some energy for it to expand. So the density of the fluid basically will go down. It's like if you if you what happens is the fluid may if you in throttling case, if you pass liquid, it may come out as a vapor and liquid. It will come out as a vapor liquid because this during an expansion the density has to go down. So what will happen is this fluid will take its own internal energy to convert to, you need a latent heat, right, to convert phase. So it will consume its own internal energy, and because of that the temperature of the fluid will go down. That's
Okay,
what
sir.
happens in the throttling case, but that doesn't happen in nozzle, because during the process that is converted to an uh, change in kinetic energy.
Okay, so is it due to the difference in the diameter or anything like for the
Yeah, you can
throttling?
call
No.
it happens only with very small dias. You need a very uh, small dias. Nozzle, you have a larger diameter compared to this small. If you see, this is a puncture, very small dia, and you can
Okay.
happens in a capillary tube, which also is a very small dia.
Okay.
Okay, so we have a, for a spontaneous process, choose the correction option for from the following expression for entropy of system and surrounding. So you have four expressions, and what is the right expression? You have a system and your surrounding. You're saying that difference between the system and change in entropy and surrounding change in entropy is greater than zero, and your surrounding change in entropy is greater than zero. And you're saying system plus surrounding entropy is greater than zero, and system entropy is greater than zero. This is for a spontaneous process. What will happen? So the answer is option C. The system and surrounding entropy it should be greater than zero. For a reversible process, this will be zero equals to zero. For any other process, it will be greater than zero. So this is the total entropy, or you can say the environmental total isolated. Assuming it's an whole universe is an isolated system. If you do any system, the surrounding entropy will may rise or fall. Your consequently, your system entropy may fall and rise, or and but the total change in entropy of this combination will always be greater than zero. So the answer is option C. So moving on.
So,
Yeah.
so for you said that for the expansion it will be an irreversible process, isn't it?
Yeah.
For pre-expansion of the gas.
Yes.
Then if we take the polytropic expansion and the adiabatic expansion, it is actually termed as reversible. Is there any reason for that?
Sorry, can you come again?
So for the free expansion, it's actually said that it will be a irreversible process. Then for the um, adiabatic expansion and polytropic expansion, I have it is termed as an reversible process. Is any reason for that difference? I mean, when I solved a problem, it's asked about the which one is the irreversible expansion. They have given the option as polytropic expansion, adiabatic expansion, and this free expansion. The correct answer given was this free expansion.
Free expansion is irreversible, right? You are asking, the options were for irreversible process.
Yes, sir. Yes, sir.
Okay. see, assume this, you have a balloon or water, you have filled that air at some pressure, right?
Yes, sir.
So now you're puncturing it and the gas is escaping.
Okay, sir.
So you did some work to fill the air inside that balloon.
Yes.
You're not getting anything out of it when it's expanding.
Okay, sir.
So in the other way around, you can get some work from in a reversible process. If you go back again, if you in the process you are expanding, if you are rotating the turbine the other way around, you are expected to compress as well. But that doesn't happen in case of uh, if, if you say simply, you have engine, you have a piston and cylinder arrangement in which the gases pushes it and you are doing some work. But if you have reciprocating type compressors as well, which is also of piston and cylinder arrangement. See, you see, you can do a compression process as well as an expansion process in that. Assuming it is an adiabatic process, you can go back in that process. But in during a free expansion, you are not doing that. You are doing some work and you are filling that air. It is expanding. You cannot bring it back again as a compressed state without doing any work. You're getting my point. That's why it's an irreversible process, but this is being a reversible process.
Okay, sir. So we need to, if we are able to reverse it by doing the work on it,
Yeah.
then it can be
See,
termed as a
that's
reversible.
the exact term. Reversible. It can go in reverse. You can, if you go in reverse, you should regain the initial state without any
Okay, sir.
change. That is what is a reversible process. That's an ideal process which you assume.
Okay, sir. So this adiabatic process, will it be a reversible, or is it irreversible? I mean, the isentropic process is termed as reversible adiabatic.
The
So,
reversible adiabatic is an isentropic process, but adiabatic process may not be reversible process. You
okay,
need
sir.
a
So,
reversible adiabatic, that is called as isentropic process. But a simple adiabatic process may not be an uh, isentropic process or a reversible process.
by terming just the adiabatic expansion, can we say that it will be a reversible?
Uh, Based on an assumption, you cannot generally say that it is an reversible process. If you are assuming that to happen to be a reversible process, then that's a different story.
Okay, sir.
But in most of the case, in the solving, you assume that it to be a reversible process. Okay.
Okay,
So
sir.
moving on. So this for an isolated system, the value of entropy will never decrease. Okay. So this is similar to the previous example, which we say that delta system and surrounding, which will always will be greater than zero, and for a reversible process it will be zero. So it's just another statement of that. For an isolated system, the value of entropy never decreases. So it can either be constant or it can be greater than. It can increase or it can remain constant. It can never decrease. So statement is true. Okay. So there's an example scenario. You have cooking. So the person is cooking food. So in a pan. So we have three cases. You have a uncovered case. You don't have your lid on the pan. You have a light lid, and third is a heavy lid. Assume it's a pressure cooker or something. The third one. So for which case the cooking time will be the shortest? Yeah. You see, the answer is option C. The cooking which with the heavy lid. So that's why you use pressure cookers on all, right? Yeah, because the cooking time also reduces. What happens is, if you see, uh, you're supplying in energy to the pan or the vessel which contains the food, and in case of having lid closed, what happens? You're trapping in water the contents inside. So the air or the water vapors and which are combination which are there inside, you're supplying in energy, so the system's energy will go increase. there's a rise in temperature which will cause the pressure to increase, and for that, at that point, your temperature is also larger compared to the uncovered case, because that the pressure is the room atmospheric condition. Here the pressure will be larger, and correspondingly the temperature of the inside the contents. So this will take very less time compared to the uncovered case, and the light case will be better than the uncovered, and the best will be the with a heavy lid. Okay, so we have a power plant here scenario. We have a high temperature source. We are running a heat engine between a high temperature source and the yeah, it's basically the energy is supplied to the heat engine from some uh, means. There's a high temperature source, so you are generating some work out of it using the heat engine, and the temperature the heat uh, you, as you know from second law, you cannot convert the whole amount of heat to work, so there will be some amount of heat which will be rejected. So this heat rejected is to the river water. So they are saying that you are generating a 600 megawatts of work from the steam power plant, and that amount of heat which is rejected is rejected to the river, and the thermal efficiency of the system or the heat engine is 40%. So you are asked me to calculate the rate of heat transfer to the river water. That is, you need to calculate what amount of heat is rejected to the river. You have four options: 900 megawatts, B 1000 megawatts, C 1440 megawatts, and D 500 megawatts. You can work it out. See, the change in difference in the heat will be equals to W. That is one equation, and you have one efficiency equation which is given. The efficiency of the system is 40%. So the 40% of energy supplied is getting converted to work. Yes, the answer is option A, 900 megawatts. So if you see the solution, the efficiency is defined as the work you obtain from to the heat which you supply. So that is the thermal efficiency is defined. So W by Q1. Q1 is the heat supplied to the heat engine. Here we know thermal efficiency, which is 40%, and we also know the work done, or the amount of work which you get from the steam power plant, which is 600 megawatts. So you have to just substitute in, and you can get the amount of energy which you are supplying to the steam power plant. So the amount of energy which you are supplying is 1500 megawatts, and as you know that difference between the energies Q in and Q out will be equal to the work done, and we already know that Q in is 1500 megawatts, and W is the work done, which is 600 megawatts. So the difference is 900 megawatts. So I hope this is clear. Okay, moving on. So does latent heat change with pressure? You know what? I would define Hg is the enthalpy of the gas, and
Yes,
Hf
sir.
is the enthalpy of fluid, and Hfg is the latent heat. I'm saying, will it change with respect to pressure? A yes, B no, and C cannot be said.
So in that there will be a dome, isn't it? So we will be having different pressure lines for different temperature. So according when the pressure changes, we will be getting the length inside the dome will be reducing. So it will be changing.
Yeah, it will be changing. Answer is yes. It will change. At the critical point, you don't have any internal any latent heat. It will straight away change from liquid to vapor. But if you are inside the two-phase dome, the you will have you need a latent heat for it to change from liquid to vapor. So I have taken a problem. This is a descriptive kind of problem. Just it may be not be similar to what the assignment problems or the exam may be, but I thought I will explain a better idea of the system thermodynamics review. So I've taken a problem on that. We have a container of a mass m of oxygen. So there is a container which is then there is a inside there is oxygen which is stored of mass m. So there is a it is kept on a horizontal on wheels. So this container is subjected to two processes. So there is two process which is happening to this container. Initially, the first process is there is a very slow acceleration. So initially, this container and the oxygen inside the container are at rest. You are assuming that this container is wall is infinitely rigid. So infinitely rigid in sense you do whatever you do, it will not deform or such. It's very rigid. So that's the assumption you are making. And the second is the container is thermally insulated. So there is a good insulation which has been also provided on the container. So the inside of the content oxygen contained in the container is contained in a rigid vessel, and it's also thermally insulated. So now this container is going in two process. It's kept in a wheel and it's slowly accelerated. It's very slow acceleration which has been given from the state at rest, initially at rest, and it during the slow acceleration process, it's reaching a constant speed c2. C2 some value of velocity it's reaching, and this next process is there is a brutal stop resulting from shock against a vertical wall. So it's going constantly accelerating and has reached a velocity. After reaching this velocity, it's going and hitting the wall, and it's coming to a abrupt stop. So abrupt stop is means there is no velocity. C3 is becoming null. C3 is 0. So that is the process which is happening. There is a two process. First is very slow acceleration to velocity c2. Second process is it's going and hitting with the shock. It's coming to a stop. C3 is 0. So that is the two process. And your assumptions are the container is infinitely rigid and it's thermally insulated. Now the data which we know is that the temperature of oxygen is 20 degrees Celsius, and you have an isochoric specific heat of oxygen, CV of given oxygen is 0.6496 kilojoule per kg Kelvin, and you know that mass of oxygen is 0.1 kg. They are saying that speed of the container at state 2. So the first process, it's reaching a velocity. So that velocity is 100 meters per second. So you are asked to determine the evolution of the internal energy and the total internal energy of the system. So this internal energy is the internal energy of the oxygen. The total energy is the combined whole system oxygen and the other parts. So what will be that in the first case? Second is there is a you need to find the temperature, how the temperature is evolving. And third case is the process reversible. The process you need to say which either process 1 and 2 is reversible, and process 2 3 is it reversible, and if you is it so, why? So that's a question. I hope the question is clear. I'll think over it. I'll also try it. I'll give you some 5 minutes. I think it's a descriptive problem. Think over it. I'll see. I have the solution. I'll give it to you in 5 minutes. You think over it and try to solve it. This may not be similar to the MCQ types which you get in the assignments and maybe in the uh, exam, final exam. But I hope this problem is a good problem and it will explain uh, your thermodynamics better. we'll see the solution how it goes. So I'll tell the process how it's happening. You see, the first process is a slow acceleration and it's reaching state C. Okay, sorry. So we'll see the solution. We have two process. The process one is slow acceleration and it's reaching state C2, and there is abrupt stop after that. So the first is saying that there is a slow acceleration means you are assuming it to be a reversible process. It's going to a multiple equilibrium points. There's a very slow acceleration. You are not disturbing the system such that there will be no any friction or something. You are assuming it to be reversible in that process. That's the assumption which they are underlying. And second, there's a shock and it's coming to an abrupt stop. So if you see, there is a two parts of the system: the whole system and the oxygen which is contained in the system. During the process, what's happening is, during the slow acceleration, the total system is having a velocity, but the internal energy of the oxygen will remain same. It's not, there is no change in, you see, internal energy of the total system will be sum of internal energy and the kinetic energy and potential energy and so on. This being horizontal, there is no potential energy is happening, but there is a change in kinetic energy. So this is contributed to the total internal energy of the system, but the oxygen's internal energy will remain same. So in that case, what will happen is, you are doing the process 1, there is no heat transfer happening because this is insulated. There is no change in volume or such. So and there, if you see, there is no heat transfer, so your entropy also will be 0 in this case. This being slow acceleration, you are assuming it to be a reversible process. So there will be no entropy generation. So this will cause your internal energy of the oxygen contained of system will be 0. There will be no change in internal energy. So during the first process, the delta U of the oxygen will be 0, but the total internal energy, you are having a change in kinetic energy of the system. So the total internal energy will be the change in internal energy of the system plus the kinetic energy and potential energy. Being horizontal, potential energy is 0, but kinetic energy from 0 you are going to C2. So mass into velocity square by 2. So that is the internal energy which is being given. So there is this change in kinetic energy is the change in internal energy of the total energy of the system. So m is given as 0.1 in this case, and you know C2 is given as 100. So 100 square divided by 2. So this comes out to be 500 joules. And then during the process 2-3, this container is going and hitting a wall and it's coming to a stop. So in this case, what's happening is, the internal energy of the total internal energy of the system will remain same. There is no change in the total energy of the internal energy of the system. But what will happen to the oxygen's internal energy, which is stored in the container? Because your now the kinetic energy is it has come to 0. This energy which was there initially with the total energy total system is now has to go somewhere. So this kinetic energy will go to the oxygen which is stored in the container. Due to this, when it went in and due to the shock and so on, this kinetic energy will dissipate into the oxygen. So what will happen is, the internal energy of the oxygen will rise in this case, but the total internal energy will be same of the system. The system, the vessel and oxygen with total will remain same. So there will be no change from state 2 to state 3 in total internal energy. You see, there is two parts. One is total internal energy, which involves oxygen and the container and so on. During the process 1 to 2, there is no change in internal energy for the oxygen, but in 1 to 2, the whole total internal energy of the system is rising because it's having some velocity at the end of the process 2. Now during process 2-3, what's happening is, this vessel is went and hit to the wall and is coming to rest. So during this process, the internal energy there, because it has reached some value of energy, so this is not dissipating anywhere else, because this being insulated and all, and the vessel is rigid, there is no work done on the vessel, anything, there is no change in volume, so there is no work done, there is no heat transfer happening because it's being insulated. So in this case, the total internal energy will remain same. But what's happening to the velocity there is no some there was some form of kinetic energy which was present at the state 2, which is not present in state 3. So what's happening here is this kinetic energy is dissipating into the oxygen. This will raise the internal energy of the oxygen. So in state 3, the total internal energy change delta U of the system 3 to is 0, but the change in internal energy of the oxygen equals to 500 joules. So it is same as the kinetic energy which you calculated in the previous step process. So that is 500. So this is just the other way around. uh, I hope I am clear in this case. You need to distinguish between these two. There's a oxygen part contained in the system and the total system. There's two parts here. uh, in first case, the oxygen is not going any change in internal energy, and the total system is going in change. There's a change in internal energy. In the second part, the total internal energy is not having any change, but the oxygen is having a change in internal energy. So that's the distinction here, and this is happening because of the process. The first process, it's a slow, being a slow acceleration, there is no change in oxygen. But in the second, being an irreversible process, the energy has to go somewhere, because it's not going to the ambient, it has to go somewhere, so it will go inside to the oxygen. So that's why it's rising the oxygen's temperature, oxygen's internal energy. So you know that if the internal energy is increasing, so it will eventually increase the temperature. So in the first process, if you see, uh, the oxygen system's oxygen temperature, there is no change. The total energy of the system was rising, but the oxygen's internal energy was same. It's not there is no change. So that being 0, there will be no change in temperature during process 1 to 2. So when it has reached velocity 100 meters per second, the temperature was same as what it was at rest. It is at 20 degrees Celsius. So that's what is happening in process. You see, that is also a reversible process as well. And so there will be no friction, nothing for it to cause any heat or rise in temperature of oxygen. In process 2-3, what's happening is you have oxygen, and that internal energy has raised by 500 joules. So this rise in internal energy will cause an increase in temperature as well. So how will you calculate that? So you know that a change in internal energy is equals to mass into uh, isochoric heat capacity into change in temperature. You know mass, you know CV, you need to calculate delta T, and D you also know that in process 2-3 it's 500 joules. So 500 by 0.1 into 649.6 joules. As you see in the previous example, it was given as 0.6496 kilojoule per kg Kelvin. Here everything is in joule, so I have kept it all in joules. So 649.6 joule per kg Kelvin. So you'll get 7.697 degrees rise in temperature. So at end of process 3, when it has reached process come to a stop, the temperature of the oxygen would have been 27.7 degrees Celsius. So that's what is happening. I think I'm clear. Is it clear till here?
Hello, sir.
Yeah.
So isn't in the second process like heat will dissipate in the in the surrounding?
That's what. See, how will it dissipate? You're assuming it to be insulated, so, and the vessel is not going any. Vessel is rigid. It's not deforming or something. In what form could the energy dissipate?
Like container is rigid and they is thermally insulated.
Yeah.
So like internal energy of the oxygen will not transfer outside, but
Yes.
kinetic energy of the system
Yeah. So
that
that's what.
may be
How in what form can it go out?
in the form of heat.
See, that's what's happening. This being the container, if it had been deformed, it could have gone some work done or something, and it would have generated some heat. Even if this thing is generating some heat, this being insulated, you're assuming that there can be no heat transfer to the surrounding.
So, I mean, the kinetic energy will convert in the form of the heat.
Uh, see, suppose what happens if you have a bucket full of water, and
Yes, sir.
you uh, give it some velocity, you pull it, and you stop it. What do you think water will? What do you think? How will you think what water will behave?
Stop with what, sir? Like hand, like just.
See, you have a bucket full of water. You're just pulling it,
Yes.
so you're moving the
Yes.
bucket. You're sliding over
Yes. Sir.
the surface,
Yes. Sir.
and you're stopping it.
Yes. Sir.
How do you expect the water to behave?
Like isn't, sir, like that uh, energy will transfer to us, our body.
See, it was initially the water was initially at velocity, some velocity, right? The whole system was at some
Yes.
velocity. Now you're suddenly stopping. The water will you will see some waves, right? It will be oscillating towards each corner, towards the
Yes.
side
Sir.
you were
Yes.
pulling. The force which you have, it'll be opposite to that, and then it'll come back again to this side, and it'll keep on oscillating till it dies.
Yes. Sir.
So in this case, there's a movement during this process. Uh, because of friction and all, the as it's not insulated, this water will release that energy to the environment.
Okay.
You're getting my point. In this case, what's happening is this system is totally insulated, and you have inside oxygen. You'll have that shock effect, and there will be a shock and moving of oxygen molecules to the container, and it will try to reject heat.
Okay. Like full system is itself insulated along with the like
Yeah.
container.
Yes. That's what the whole container is. The container is insulated. That's the case. And the container
Like
is rigid and
in,
it's insulated.
so there will be like all the system is like in the form like insulated means there will be no any heat transfer from outside to the, like
Yeah,
the
not from
system.
outside and not to the outside or from the outside.
Okay, sir,
See, that's
understood.
what's
I have
happening process.
confusion. Like I
There is
was
no delta
thinking
Q.
only oxygen is insulated and oxygen is insulated, and the energy from oxygen can't transfer to the surrounding, but like
Yes.
from the container transfer. Okay, that
Yes.
was confusion. Thank you,
Yeah.
sir.
So you just remember that bucket. You see the oscillation. The same similar thing will happen to the oxygen also. But this change in this thing, it cannot dissipate anywhere else. So it will increase its own internal energy.
Okay, sir. Thanks.
So that's the rise in because there is an increase in internal energy. There is be a rise in temperature as well. And you see, the third part was whether the process was reversible. So the first process is the system goes through a succession of mechanical and thermal equilibrium. So that's what in reversible process you said very slow acceleration. So it's going that's like a quasi-static equilibrium process, which you would have studied. So you assuming that in the piston you keep small grains of weight for it to compress. So there you can also remove small grains of wood to expand, right? So that kind of an ideal reversible process. So similar thing is happening is being assuming it's a very slow acceleration. The system is going through multiple equilibrium points, so you can bring it back to also. So the process 1 2 will be reversible. So and how will you prove it mathematically? There is no temperature rise of the system. So in this case, there will be no entropy generation. There is no change in entropy. So temperature is being same. You can find that change in entropy is expressed as mcv ln T2 by T1. In this case, there is no change in volume or no change in pressure. So the other part will be 0. So there will be mcv ln T2 by T1. So T2 being equal to T1, the delta is will also be equal to 0. So the first process delta is equal to 0. So you can say that also it goes to multiple equilibrium very slow acceleration, that this will be a reversible process. Second case, process 2-3, you see that there is a rise in temperature. So following the shock, what will happen is oxygen subjected to pressure waves, and because of that shock there will be pressure waves created, which will progressively damp out because of the friction of the fluid. There will be some, because of molecules getting eating each other, so it will that will die out, and this will increase the internal edge of the system. That's what I told you, the waves forming, the bucket water oscillating and also. So in that case what happens is, this will increase the increasing the temperature. So this process is irreversible, you know, the you cannot create the same, you cannot go back to the initial position same. You have hit the wall and it's come to a stop, you cannot reverse this process, right? Even ideally also you cannot reverse this process, you cannot go and hit the wall and come back, so that's not possible. So that is definitely an irreversible process. And you also mathematically you can see that this being a rigid vessel, and uh, so and this being a closed system, there is no volume change. So you can see that delta S is mcv ln t 3 by t2, and you know T3 which is 27.7 and T2 20 degrees Celsius. You put it in Kelvin here. You have to put 277.07 plus 293, sorry 273, and so for T2 also you put it in Kelvin, and then when you substitute you'll get 1.684 joule per Kelvin. So that is the change in entropy. So this will show that this process is irreversible. What I've done is I've expressed this process in a US diagram. This is internal energy on the y-axis, entropy in the x-axis, to just get a feel of what's happening. So in the process 1-2, what's happening is your internal energy is remaining same. This is for the oxygen. So oxygen, this thing is remaining same, and but you have U3. U3 is a or the system internal energy. You will have some kinetic energy that is being added to the oxygen internal energy. So there is a total energy of the system. So what's happening is in 2-3 is this being constant. U3 U3 is constant. Do I get a pointer? Okay, I don't have a pointer. Okay, so this horizontal line in U3 at the top line, that is the constant internal energy line during process 2-3. So that is remaining constant. You see this is going through a velocity change. This is a change in kinetic energy is expressed as the vertical lines. So during 2 to 3, you see velocity initially was at C2, and 3 it has reached 0. This velocity is getting kinetic energy is transferring to the fluid, and it's going through the process, and it's reaching the final state is the internal energy of the system is equals to the U3. So as you can see, during 1-2 there will be no change in entropy also. 1 and 2 lies in the same state, and 3 there is an increase in entropy, and you see there is also increase in internal energy. So that is the process is happening. I hope this problem is clear. Okay, that's all what I have prepared for today. If you have any doubts, you can ask me. I will be helping you out with. This video I'll upload it in YouTube, and you'll get a link for that. And if you have any other queries, you can ask. But please don't ask on the current assignments that you have to solve. I cannot help you with that. And Francis, you can ask you please go through the videos. If you have any doubt on exergy, you can come back again.
Okay, sir.
So this session will happen in every week.
You'll have every week Tuesday 6 to 8 is the time. I'll similar case kind of I'll have some MCQs similar to your assignment problems. I'll have some problems we'll discuss, and you can also ask on the videos on the lecture assigned lectures. You have any doubts, you can ask that as well. I'll try to clear that.
Okay, sir.
So this is generally a problem solving session, but if you have any specific doubts, you can ask that as well.
So actually, for this course, there is other two sections I have already conducted. So there will be three different sections.
Sorry, two sessions in the sense.
I mean, for the this is actually for the applied thermodynamics courses. Need.
Yeah.
Uh, I have already attended another two sections for the same course on last Friday, and
Okay, it may be
yesterday.
a different course number. This is applied thermodynamics conducted by instructors Niranjan Sahu and Mondal, professor. This is from IIT Guwahati. You would be attending some other applied thermodynamics course offered by some other IIT, I guess.
Okay, sir.
This course has two people, and I think both of us are conducting on Tuesdays, I guess. So you can attend either of us, and I think both of the videos will be available for you on YouTube. You can refer that.
So this YouTube link will be in the NPTEL portal, or it will be shared later in the chat.
Yeah, you'll have that in the NPTEL. You will have this PPT also. You can go through that, and you will also have a YouTube link, which you can go and see the videos. If you have any doubts, you can see that as well.
Okay, sir.
So there is simultaneously two links, for like the
Yeah.
same two sessions from six. What is the difference in two sessions?
See, this is conducted by two sessions. Based on the number of people enrolling, I think they assign people as such, and you can attend either of the sessions, and you can get your doubts cleared. It's just to cover the number of people who have enrolled. Expecting the number of people enrolling, there is expectation that people have doubts as well. So to clear that, they have been assigned to for this course. Generally, it can be one, but some cases there where courses people enrolled are more, they'll have two. So you can attend either of the sessions. You will can get your doubts cleared.
Okay, sir. Thanks.
Okay, then I hope there's no other this thing. Then we can close the session. Actually, no one else is also joining. Okay then. Okay. Thank you.
Okay, sir. Thank you,
I'll
sir.
meet you guys next Tuesday. If you have any doubts on the week 2 session, I'll conduct some problems on the week 2 related to week 2 on the Rankine cycle, and we can, if you have any doubts on that, we can discuss on that. Okay.
Thank
Thank
you,
you.
sir.